Hello and welcome to this video lecture. In this lecture, we will introduce aspects of the class, specifically the idea of modeling and simulation of dynamic systems. So, what are we looking at when we are discussing this idea of dynamic systems? Well, as you might have seen, up to this point, your classes have pretty much focused on one of two analysis results. And that is a system response. In other words, what is the system doing? System response that is valid. For only one point in time. And so in dynamics, you saw this all the time. Trying to figure out what forces might exist or what acceleration you might have, either linear or angular, immediately after release. How many times were you working with problems where something was happening immediately after release or immediately after something else has happened? Or when the system is at a particular state, such as a pendulum is at 30 degrees. You can analyze what's happening at that particular point in time, and that's what dynamics focused on. Or in some cases, you might be given, if you were doing energy approaches, you had a state one, you had a state two, and you would try to analyze what was happening at that particular state, that second state generally. And so, but no matter what, all of those were at one particular point in time. Another classic analysis result that classes focus on is for the steady state response. And so, of course, what does that mean? That means that when any kind of strange things die out and you're just left with a response that persists throughout the rest of time, assumed to go off to infinity. And so you can see that these particular analysis approaches are pretty restrictive. Here, I'll say that these are severely limiting. Not that they aren't important, but it is, if that's all we were left with, that would be very limiting because, of course, system responses typically evolve over time. And it's important for us to be able to appreciate how that system response is evolving over time, because even though the steady state response of a system, what happens as after everything kind of dies out, all the strangeness dies out over time, as you'll soon see, we'll call that the transient response. So after the transient response dies out and you're left with the steady state response, you might have a perfectly acceptable steady state response, but in getting to that response, the performance may be completely unacceptable. So one example that I like to use is if you are trying to control the temperature in a room, maybe the room you're in right now, uh, and we're trying to, let's say it's a relatively cold day, and you're trying to warm up that room, and let's say you're only going to be in that room for an hour for the duration of whatever lecture we might be discussing, whatever lecture topic we might be discussing at the time. And so somebody comes in the room and says, okay, we're going to warm up this room, and they stick a single candle in the middle of your desk, burning, thankfully. So they stick the candle in there, but the room is freezing cold. How long is it going to take for that candle? Well, first of all, the question is, can the candle heat up the room eventually to a temperature that might be okay? Well, if the room's well enough insulated and things like that, yeah, maybe eventually, though, to be honest, you're probably more of a heat load on the room than the candle is. But to kind of go with this example, maybe eventually the candle will heat up that room if it's a big enough candle. In other words, it will burn long enough. Maybe eventually it will. But by the time that candle heats the room up to a temperature that is at least remotely comfortable, whatever event you're doing in that room is long gone. So, and you may not even be in that room anymore, such as if we're dealing with a classroom. You may be long out of that classroom, and meanwhile that candle is still trying to heat up the temperature of that room, and it's still going to be freezing cold in that room by the time you have to leave. So you can see with how slowly, so sure, we have a solution at steady state. Maybe that candle, and I guess we can't have a perfectly insulated room then if we're dealing with steady state, but that's a different, that's for heat transfer. How does that sound? So let's say it's not a perfectly insulated room, but eventually that candle will be able to produce enough of an output that it will heat the room up to a somewhat comfortable temperature, but it will take so long to do it that it's essentially meaningless. And so you can see that even if we assume in the steady state that the candle can finally get the temperature of the room to something we want, it takes so long to do it that it's effectively a failed solution. And so, and the argument there isn't that the candle couldn't do it, it's just it couldn't do it fast enough. Oh, well, that's the evolution, right? That's where we're talking about the transient response of the system. So you can see that if we don't have the proper transient response for a particular problem, then our solution can be considered an abject failure just as much as if the temperature of the room was never controlled by the candle at all. So it's one of those things where the transient response of the system is just as important in most cases as the actual steady state response. So you might say, well, that's nice, but yeah, I mean, when are we ever going to be dealing with a steady state response? Or I'm sorry, a transient response? Well, it turns out that all real engineering systems, so sure, our conceptual ones may not have a transient response, but all real engineering systems have a transient response because things in the real world can't move infinitely fast. They don't have infinitely little mass, thermal mass or inertial mass or whatever. Things won't change instantly, and because things don't change instantly, they have a transient response. So of course, that means that if we're going to do a proper job of engineering a system, we need to properly understand that transient response. So here I'll say it in order to properly understand the nature of the system, clearly we must be able to capture the transient system response, or the transient response of the system if you prefer, either way. Now, of course, the transient response of the system will decay away, essentially by definition, for engineering systems. And we'll discuss that a little bit more in the future. And then when it decays away, then we'll be left with a steady state response. So that's not to say that we're not interested in the steady state response. We, of course, are, because if the candle, going back to the candle example, the candle can never get the room to a comfortable temperature, we've already failed even on the steady state response, as well as failing on designing a system that will provide an acceptable transient response. And so we failed pretty much across the board at that particular point. So we are still interested in the steady state response, but since most of your other classes focus on that, this class will generally be focusing on the transient response of the system so that you can then capture what's happening not only as the system response is evolving over time, but also what will happen once that evolution has steadied out into a constant, a particular constant response. So here we need to clearly, if we're going to understand the transient nature of the system, so to understand that, we need, or well, I guess the question is, why do we need to understand it? So if we don't understand the nature of the system, either steady state or in our particular case for the transient response of the system, what are we doing? Well, then we're trying, as indicated in prior lectures, we're trying to effectively design or work with a system we don't understand. And if we don't understand the system, how are we going to design that system? And clearly the answer is you can't. There's no way to design a system or work with a system that you don't understand. So here I'll be kind and say virtually impossible to do, but I think you could easily argue that I could even eliminate the virtually and just say that it's impossible to do. So as we have seen then, and as I've indicated, generally your classes so far, still on eraser apparently, sorry about that. So as we can see, classes up to this point have only given you, if we want to call it that, half of the picture. Really the steady state half, or the ability to analyze what's happening at one particular point or one particular time. So this class, of course, will fill in the picture by, of course, focusing on understanding and predicting the transient response of a system. So let's go ahead and capture the modeling of a dynamic response. And again, this is just going to introduce the idea and give you an idea, or introduce the concept and give you an idea of what we need in order to model the dynamic behavior of a system. And when I say what we need both from a mathematical perspective as well as from a physical perspective. Here we'll focus on the mathematical perspective, because again, what is modeling all about? When we talk about modeling as engineers, we're generally talking about developing a mathematical statement or series of mathematical statements that allow us to capture our best understanding of how a system will respond. So let's go ahead, or how a system behaves might be a better way to say that. And of course, why are we trying to figure out how a system behaves? So that we can figure out how to impact that behavior if it isn't behaving how we want it to, i.e., we can design the behavior, we can design the system, let's say it that way, so that it behaves in a particular way. And without having a mathematical model, and not without having some understanding of how that system's going to behave, there's absolutely no way we would be able to design a particular system behavior, because we don't even know how it behaves. So modeling, let's go ahead and capture that first. So that's developing a mathematical description. We'll do the TION down here, mathematical description of a system. Now, we can capture the mathematical behavior, or the behavior, let's say it this way, empirically, and here I'll do an or, but really it could be an and or, from first principles. So what do I mean empirically? So Empirically, we go out, we have a similar system where we can vary a bunch of different parameters, and we test that system in all sorts of different ways, figuring out how it behaves, figuring out how those behaviors relate to the different changes we imposed on that system. And then we can develop tables, we can develop charts, we can develop graphs that allow us to say, as we change this parameter, this is how the output of the system changes. In some cases, we can turn those graphs, tables, charts into equations. And so we can deal with best fit equations, which is another way to approach it. But those equations are developed from the, or derived from the empirical data itself. And in that particular case, we aren't necessarily as interested. If we can, it's great. If we can tie what's happening to that system to basic physical concepts, that's wonderful. But that's not necessarily the end goal of that effort. The end goal is just to say, this parameter was changed, and this is how the system responded to that change. And that's really all that's trying to be captured, not necessarily the concepts behind how that's happening. Now, again, if we can capture that influence or that relationship through our concepts, that's even more powerful. But that's not necessarily what we are aiming to do at the outset in most cases when we're trying to empirically establish the behavior of a system. First principles, of course, are where we have these concepts that are then related to other concepts, and those relationships are captured mathematically, such as F equals ma. Force, mass, acceleration, those are all concepts developed by human beings. And so thankfully, somebody, namely Newton, was able to come up with a relationship between those various concepts. Force is equal to the mass times that mass's acceleration. And so understand that you can't derive first principles. What happens is that those principles are just tested time and time and time again, and they're shown to pretty much capture what's happening in the physical world. Now, of course, in some cases, those first principles start to break down at the edges, such as getting close to the speed of light. Then other things start to happen. But, for the most part, for wide ranges of behaviors, those first principles have been proven to be correct. But again, they've been proven that way. It wasn't that somebody went out and derived the first principles. It's just somebody, in this case, Newton, for F equals ma, came up with it and said, this seems to make sense. And here are the tests that show that it makes sense. And then it just kept getting tested over and over and over again. So you can actually see that first principles are just foundational empirical relationships. So in reality, you can say, everything's empirical. And that would probably be true. And so first principles then we can say that first principles are more aligned to having concepts attached to them than are other empirical efforts. And so for first principles, we're really trying to attach concepts to the different quantities and how those quantities relate to each other. And in the purely empirical efforts, we're not really as interested in that unless it just happens to come out of the data. So with that, and honestly, here's one thing that is important to recognize, is that which would you trust more, first principles or empirically derived data for something that is very closely aligned to what you're doing? Obviously, the empirical data, right? Because that's going to capture not only the primary effects and maybe even some secondary effects, but the empirical data, which would also potentially be captured by the first principles. But you're going to capture even more subtle effects that the first principles either assumed away or couldn't even contemplate trying to account for. So understand that generally empirical data is better data to work with than our models derived from first principles. But nonetheless, in the absence of anything, first principles are really the way to go. And it turns out that first principles, working with and deriving models based on first principles, are very efficient, or that effort is very efficient, which is why we do it time and time again as engineers. So you're going to be dealing with first principles when you get out into industry. You're going to be dealing with empirical data when you get out into industry, and you're going to be dealing with a blend of the two, where you have empirically modified equations that came from first principles. So you're going to see a blend of just about everything when you start talking about working with this stuff from an engineering perspective. So let's go ahead, and now that we understand kind of where our information is coming from, where our relationships are coming from, let's go ahead and capture this idea of modeling. And this modeling, of course, allows us to capture our understanding. Clearly of how the system works. And so that's the whole point, because we know that when we're dealing with a particular mass, that mass is going to react in a specific way. And so these mathematical models allow us to capture that this mass can't go and do any random thing that we can dream up. It is tied to, and its behavior is tied to very specific physical principles. So these models allow us to capture how the real world will work and the limitations associated with those real behaviors. And so that's going to give us an idea of how these systems behave. And then once we have an understanding of how these systems behave, then we can start designing a particular system or modifications to an existing system that will give us the behaviors we want, including the transient behavior. So getting into the transient behavior, we have a dynamic system. And so a dynamic system is a system whose output, and here I'll use just a particular case, whose output evolves over time when subject to the sudden application of, here I'll just have a constant input. So let's say that we might have some voltage and the system's just hanging out. So we have some input voltage, the system's hanging out at that input voltage. Everything is, all the voltages are fixed throughout the system because that voltage has been applied for forever. Let's say that maybe it's 5 volts. And then at a particular time, we say, great, now we're changing it to 10 volts. So now we have a sudden application of a change, but a constant change to the input. And then what's going to happen? The system's going to respond in some way where the voltages across whatever electrical system we're dealing with, the voltages are changing in time potentially, and then eventually those voltages will steady out as well. But clearly, because we disturbed, if you want to call it that way, the system, all of a sudden the output is going to start changing in time and evolve in time. So what's an output? Let's go ahead and capture that. So an output is the system response of interest. And and here we'll just say single input, single output, though you can easily imagine for complicated systems, we're going to have multiple inputs and multiple outputs. But when you get into control theory, you're generally going to be dealing with single input, single output systems, otherwise known as SISO systems. And so for this class, which I frankly have probably already said, but if I haven't, I consider this to be pre-controls. So here we're just going to constrain ourselves to single input, single output systems where the output is the system response, the single system response, or the single state of interest, if you prefer, and the input is the excitation. Now, there are ways that we can model what's going on with multiple inputs and multiple outputs, but that's going to wait maybe until a little bit later in your college career, if not to your graduate days, your graduate study days. And so the input is the excitation that, of course, what can cause a change in the output. So as we can see then, eh, I think we're okay. I don't know what's going on there. So we can see that the output state and the response of that state, if you want to tie together the idea of state and response of a dynamic system, clearly changes as the time changes. Oh, that's kind of interesting then. Because we've kind of heard this language before. So clearly, if we're interested in how one thing's changing as something else is changing, isn't that exactly what we're interested in, or we were interested in when back in your math days when you were discussing derivatives? And so as I indicated, one of the most important things to understand when you're starting in on studying a new discipline is the math, the foundational math, and how the foundational math for that discipline properly captures what you're trying to describe in that particular discipline. And here you can see it perfectly, right? We have a change in the output as time goes on, capturing the evolution, the time evolution of that output. And then, of course, if we get to a small enough time scale, then we can say that we're down at the differential realm and we get the derivative of the output with respect to time. So clearly we can see how that output is changing as time is changing. Now, of course, what does that mean? Well, for dealing with derivatives, we may deal with derivatives of different orders, and we might be able to relate those derivatives to each other. And so you can see that if we're trying to figure out how things are changing in time generally, that the way we're going to do that is with differential equations. Because using derivatives and relating derivatives is obviously, and even conceptually, you can just see it, is obviously the most appropriate way to work with these dynamic systems. And so that's going to be one of the main thrusts of this class, is working with differential equations. So we'll talk about differential equations just from a purely mathematical, purely abstract perspective initially, and then we'll start tying those differential equations to real systems and the behaviors, or models of those real systems might be a better way to say it, and the behaviors of those models. And so that's the point of this class, is to work with those differential equations and the models captured by those differential equations to understand how the transient response is changing. And we can even use those differential equations to determine the steady state response of the system as well, because that's also very important to know. And so you can see then, hopefully through this discussion, that again, the idea of working with differential equations is central to understanding what's going on with dynamic systems. And the reason it's central is because, mathematically speaking, that is the perfect mathematical tool to capture what's happening with the dynamic response of a system. So with that, we'll call this video lecture a wrap, and the next video lecture, of course, is going to start in on our discussion of differential equations, now that you have an understanding of why they are so important to this particular discipline, this particular subject within mechanical engineering. So with that, we'll call this video lecture a wrap.